My name is Carlos Lazarin, and during this session, I'm going to talk about the key aspects to design a modern scalable system. This is our Tech Week 2024. So this is our agenda. I'm going to start with architectural drivers. Then I'm going to jump to large-scale systems architectural building blocks. Then software architectural patterns and styles, and our final thoughts. Architectural drivers. So I invite you guys to think about the answer of these questions. What do we need to build? And the answer is going to provide us the architectural drivers for our system. So it's all about requirements, right? So we do need to understand what our customer needs. And we have three types of requirements. We have functional requirements, we have non-functional requirements, and system constraints. So the functional requirements define what our system should do, right? Given a specific input from users, so our system is going to process something and provide an output. And having that in mind, we can create a use case with the actors and the system interacting together, right? And how can we collect those functional requirements? We can have brainstorm sessions, interviews, observation, workshops, servers, prototyping, and etc. Then we have the non-functional requirements, and they are the general properties of our system. We can call that like quality attributes of our system. We have scalability, availability, resilience, and fault tolerance, performance, SLAs. I'm going to talk a little bit more about them in the next slides, don't worry. And then we have our system constraints that limit us, right? The limits. So we have technical constraints. So maybe our team does not have enough knowledge in a specific technology, or we need to work with a specific cloud provider, right? And we also have business constraints. We have a limit deadline that we need to follow. It's a short deadline or a budget limitation. Also, we have some regulatory legal constraints. Some countries have some laws that we need to follow, and this limit our design, right? So moving forward to non-functional requirements, the third thing that comes to our mind is scalability. So this is the property that our system needs to handle a growing amount of work in a cost-effective manner, right? And what if our system has 100 of users or 1 billion of users accessing the application at the same time, right? And if you have heavy videos, have images, etc., so we need to have a big server, right? To have enough capacity to handle this kind of situation, right? So we have two types of scalability. We have vertical scaling. So when we have a big server, if we can increase the CPU power and we can increase the memory, for example. But we have a limit, right? At some point, we're gonna hit a wall or have a physical limit here. And of course, doing that, increasing the server itself is not enough because we're going to have a single point of failure. If our server goes down, it might be powerful, but if it goes down, we're going to lose our application, right? On the other hand, we have horizontal scaling, where we have multiple services working together, coordinated by the load balancers, right? And it's a better approach because doing that, we have fault tolerance. We can mitigate the downtime of our service. If one server goes down, we have other server to take the job, right? And we have an infinite way of scaling, depends on the amount of money we are open to spend, of course. And one important point to keep in mind, our application needs to be stateless. So one server needs to work independent of others, right? We cannot have a stateful application in this case. So which one to choose? So it depends of your requirements. Again, right, if you have application that's going to receive up to 50 users, why we're going to have a horizontal scaling approach? It's too much, right? So those are things to keep in mind. What about availability and fault tolerance? So availability is the capacity of our system to continue operating with the minimal risk of failures, right? So in this case, for example, this diagram illustrates a situation that we have a user accessing our application over the internet, and we have a load balancer that is going to coordinate which service should receive the request in that moment. I'm going to talk about a little bit more load balances later, but as a kind of situation that we can provide high availability for our users, right? And what if we have a service interruption? So what if we have a natural disaster? Our application is hosted in North America and we have an earthquake there. So we need to have a replica servers in other geolocations to take over the job, for example, in South America, totally different geolocation, right? So we have a standby server there ready to take the action and continue processing the requests that we're going to receive, right? Doing that, we're going to limit the single points of failure, and our application is going to be available the most of the time. So availability is also measured about a percentile that is defined by our SLAs, that are service level agreements. It's kind of contract that us service providers do with our customer, right? So if you are talking about a high available system, we might be talking about not 99 of availability. We're going to have 99.790 of availability, which means that we're going to have at the maximum 31.56 milliseconds of downtime per year, or even 86.40 microseconds per day, right? But if you don't care too much about availability, if your system is not critical, like aircraft one or a hospital one, it's just a simple application, you can have, I don't know, 2 nines of availability. So our application is going to be up 99% of the time. So it's going to be 30.65 days and 7.20 minutes of hours per month, and etc. And at the maximum, we're going to have 14 minutes of downtime per day, right? So it depends the type of system you're building or designing. And what about performance? So how fast is fast enough, right? There is a study that says that if a user waits up to 3 seconds to load a page, the user is going to leave our application. So how can we improve this response time? A common approach is to use CDNs, that are content delivery network. There are servers located across the globe, close to users, so we can cache static content like video, images, JavaScript, HTML pages, right? So let's say here, for example, we have our original server located in New York, and we have users in Australia consuming our application. So then we put edge servers across the world, so the users can hit those servers instead of the original one, right? So doing that, we reduce the bandwidth consumption, we improve the availability, because if the main service goes down, we have other ones to take the request and provide a response, right? Some marked options that we have: AWS CloudFront, Google Cloud CDN, and Microsoft Azure CDN. What about improving RDB? We can also have that cache in RDB later, right? It's more appropriate for applications that we have more reads than writes. In this case, we can use like Redis, Memcache, Bcache. But on the other hand, we have challenges, right? We have some hotspots. Let's say you have keywords that run more often than others. Also, we need to pay attention to expiration policy for a cache. If the expiration policy is too short, why are you using a cache, right? It's gonna expire too soon. Also, a code start. How are we gonna load the cache the first time? Are we gonna overload our servers the first time that they are populating the cache? So those are things that we need to think as well. So moving to large-scale system architecture building blocks. So what we're going to use to design our scale architecture, right? As I mentioned, we have load balancers that can help us optimizing the high volume of traffic. So they also protect us against downtime. And we have some types of load balancers. We can have load balancers that route the traffic based on IP address, based on the DNS, or also a geographical location, a global server load balancers, right? And those load balancers, they use some kind of algorithms, and I can mention a route robin algorithm that picks a server handle, right? We have a weighted round robin, where each server, the server that has higher capacity is going to have a higher weight, and then the traffic is routed based on that. And we have least connections, so the algorithm is going to pick the server that has less connections at that moment. And we have weighted least connections, that we're going to have the servers with higher capacity and less connections at that given moment. Right? And what about the DBs? What about SQL or non-SQL DB? So it depends how we're dealing with our data. If we have a well-defined data structure, tables, and normalized data, we should go to SQL DBs. And because we can run complex and flexible queries, we can perform joins, right? And also, if we care about transactional support, like bank institutions, SQL database follow the ACID principles: atomicity, consistency, isolation, and durability. So it might be our case to choose a SQL DB. On the other hand, if you have a a data that's not structured, and we need to have a more flexible and easy to scale application, scale horizontally, we might need to choose a NoSQL DB. And we have some types of NoSQL DB nowadays. We have key value store DBs like Amazon DynamoDB. We have document store DBs like MongoDB, it's pretty famous, right? And we have a graphical database as well, which organize the unstructured data in graphs and create the relationships between them. So we have Amazon Neptune and Azure Cosmos DB in this case, right? So when choosing RDB, we also need to take into account the CAP theorem. So it states that we cannot guarantee consistency and availability over partition tolerance. What does it mean? So let's take account this example here. We have a service A and a service B. They share this data set here, those database of those replicas, and service A is writing to this node at this time, and service B is consuming from here. So it's copying the data over the replicas, but suddenly we have a outage in the network here, right? So in this moment, service A is going to continue and write to those replicas here, but the service B will not consume the most up-to-date data. So that's about this CAP theorem. So we can need to choose what are more important for you. So let's say if you want to have consistency and availability at the same time, which means that we're going to have the most updated data and available all the time, you might need to go to a MySQL or SQL Server or Oracle DB. But on the other hand, if you want to have a horizontal scalability and you don't care if the data is the most updated one, but it's available, right? You can hit the database, but it's not the most updated one, but you still can read. You can go to Cassandra DB or DynamoDB. Those DBs provide this kind of feature for us, have high availability and partition tolerance. But if you want to have consistency and partition tolerance, you might need to choose MongoDB and Redis or Apache HBase because, okay, if you lose a node, in this case, you might need to wait a little bit to have this node back in order to have the most updated data again, the consistency, right? This is a nice theorem to keep in mind. And how we can improve the SQLDB's performance scaling, right? We have a common technique that's called database sharding. So it consists of splitting our data across smaller chunks called shards, right? So it enables parallel processing of our smaller data sets, and also helps us to achieve horizontal scalability and fault tolerance, because if one shard goes down, we'll have another one here to provide data, right? And we have some keys to split the data. So I'm gonna illustrate here the hashed sharding, how it works. So we have here, for example, a table, and we apply a hash function on it. So we are gonna have row A and C if a hash code of 1, and rows B and D if hash code of 2. So we're gonna move those records for specific shards based on those on the result of this hash function, right? We also have some challenges. We might have some data hotspots, some shards that are more accessed than others. And also it's complex to maintain this kind of structure, right? When we're splitting the data. Also increases the cost because it depends on the amounts of shards that we're gonna have in our solution. Moving forward to software architecture styles and partners. So we have the microservice architecture that's pretty famous nowadays. So in the past, we had that monolithic structure, right? A huge code base here running a single server in a single DB. It was hard to maintain. We had a lot of folks or a lot of teams working the same code base. If service goes down, we would lose our application, right? And then we move forward to a new architecture partner that applies the single responsibility principle. So we have independent microservices working together in parallel. So we have, in this case, for example, an image service, and a user profile service, and a billing service. And if with a specific database to each one, and if one service goes down, our application is still able to consume other service, right? So it's going to be available until the other features of the application is going to be available, and we will not lose everything. It's also easy to maintain, smaller code base. We can have different teams working different parts of our solution, right? Event-driven architecture is pretty famous nowadays as well. So it's run by events. So we have the message senders and the message recipients, that are consumers. It's all about having asynchronous communication. And it's good because with this approach, we are able to absorb traffic spikes and have high scalability, right? So I'm going to illustrate the usage of this architecture in this solution here. Let's say you have a booking hotel room system. So the users can come here and book a room, right? And they don't need to wait until the request completes. So the front end application is going to publish a new message to a RabbitMQ or a Kafka server, and then it is, right? So we have this fulfillment service that's going to consume those messages. And then you can call billing service, can call reservation service, and then later can call the notification service that's going to notify the user that the operation was successful, right? And also we can have a second message broker here down that is populated by the fulfillment service, and have analytics service consuming this event, those messages again, and providing reports to the management team, right? This is an example of event-driven architecture. And we have other pattern that's called Common Query Responsibility Segregation Pattern. That's a pretty long name, CQRS. So this is about having different models for writing and reading, right? So let's try and avoid conflicts, because those operations can conflict between them and increase the speed of our database or our operations, right? So let's say this example here. So we have a service A that writes to a DB that's optimized for writing, and we have a service B that reads from a database that optimized for reading. So we have our application that calls each side, right? So when it needs to writes to this service, and this service provides the updates to reading service through a message broker or Apache Kafka, whatever, right? Through events. So this way you can optimize the reading and writing operations. The same with this solution here. Here we have a different example, but in this case we need a materialized view of data. We need to have a join, right? So it's tough to do joins of SQLDBs, not possible. So no SQLDBs, sorry. So in this case, for example, we have a e-commerce marketplace, and we have a service here, that's product service, that consumes its own DB, and whenever we need to update our read information from the service. And we have the review service of a product, the same. But both servers have a message broker here in the middle that will have a product search service that is going to consume both sides information and update the join database, let's say that. So this database has the product search data. So whenever a user needs to search for a specific product, goes to this service that already has the product data and the review data, right? This is about the CQRS. And moving to final thoughts. So those are the steps that I would like to share about creating a scalable system, right? So just keep in mind that it's all about collecting requirements, functional, non-functional constraints, refine and integrate our customer. Once you have a solid requirement, you go to your preferable tool and create a software architecture diagram. And then we start refining this diagram, making trade-offs, which means that what's more important for you: scalability, availability, fault tolerance, and etc. So you refine your diagram, and that's it. That's it, right? There is no unique way to create a system design. Just keep creating and making the possible trade-offs. Yeah, that's all that I'd like to share with you guys. Here we have a QR code to provide the answers for a server to collect their feedback from you guys. And thanks so much for attending this session.